this webinar on thermal remedies of chlorinated solvents here in Denmark. My name is Thomas Larsen and I am Technical Director here in the WSP, working in the Department of Contaminated Soil. Before we go on, I would like to point that you can download the talk here, the slides after, in the handout box, and you are able to pose questions for me after the talk is finished by typing them in the question box. This first picture here shows to the left an example of thermal remedies that we carried out some years ago using thermal conductive heating, and the other picture here was an experiment we did some years ago too, trying to destroy extracted PCE in a flame that was used for heating up the soil. The agenda that I'm going to talk from today is a little bit about the thermal mechanisms, when and how to use these techniques, and especially also looking at sustainability by addressing carbon footprints. And I'll show you 3 examples from remedies that has been performed in the past, and we'll go over some of the pitfalls and lessons learned and wrap up with conclusions in the end. And what we are dealing with is what you can see to the right side here, the sense of the past. This is a drum storage on bare soil from that was carried out in the 70s. And actually, a thermal remedy was carried out at that particular site there. In Denmark, we rely totally on groundwater for our drinking water supply, so we have relatively strict guidelines related to what we have to achieve doing the remedies. So that's one of the reasons that why we are using these techniques. Just a short introduction here for those of you who are not familiar with thermal remedy. To the right, we have a small sketch here, and we have some kind of system that we'll go through in a minute, where we can inject energy into the soil. And then we have an extraction system that extract vapors and liquids from there. That is run through a heat exchanger, as you can see, and liquid and vapor is separated from each other, and then the vapors are treated and the water are treated before discharge either into sewer system or into the atmosphere. And normally the cleaning that we use here in Denmark, at least, is the granular activated carbon in some carbon vessels. The temperature regime we are working at when we are treating chlorinated solvents is around 100 degrees C, as you will see in a short moment. There are a lot of mechanisms that are acting positively when you're heating up the soil, and all of them tends to get the compounds from the sorbed or the liquid phase into the gas phase, and thereby making them possible to extract with a vacuum system. And I should emphasize especially the steam drive, that is point number 5 here in this list on the left side, because if you want to go to sub ppm levels, you have to be sure that all the soil that you're treating is boiling, and the steam drive is caused by the fact that when water expands from liquid to steam, it increases volume of about 700 times, thereby creating pathways for the gas to get up to the surface and be removed by our extraction system. So when are we using thermal? It's only always in the source zones, and here in Denmark, it's relatively cheap to excavate and treat offsite. So the only places where it's economically feasible compared to other relevant techniques is typically below buildings or other valuable infrastructure, and if the contamination is deep, and by that I mean more than 10 meters down into the soil. It can be used in a lot of different settings, as I will show you some examples of in the next couple of slides. And it can be used either if there's free phase or high concentrations in the soil. It can be used both in saturated and reduced zones, and it can be used for a lot of compounds in this type of application up to around 150 degrees in boiling point. The normal three different methods that we have at our hand is injection of steam, electrical resistance heating, and thermal conductive heating. I'll show you an example of each of these techniques in the remedies I'll show you in a couple of moments. In order to be sustainable, we have to think about that. And one way is to use biogas or wind or solar power for these energy sources. But another thing that is very important to keep in mind also is that we have to reuse as much of the steel equipment that we normally use as to reduce the carbon footprint. The little graph inserted there, you can see how much energy we normally has to apply from a theoretical standpoint, and if the soil is very wet, it's somewhere in between 150 to 300 kilowatt hours per cube meter. Then I'll show you some examples that we have been involved in one way or another. The first one is the oldest, where we used steam enhanced extraction, and it was a contamination with PCE that originated from a former dry cleaner. And at this particular site, the geology is relatively well sorted coarse sands, and the groundwater velocity here was around 100 meters per year, and the contamination was down to approximately 40 meters below ground. And the highly contaminated zone that we had to treat there was around 800 square meters. The goal of the remedy was to reduce the mass flux more than 95%, going from approximately 90 kilo per year to less than 5 kilos per year. The setup at the site included 10 injection wells with steam and steam air, and a lot of wells for hydraulic control, vapor extraction, and so on. And the main parameter that we monitor when we're doing these kind of remedies is the temperature, and these are just a plot of the temperature wells you can see here. And we also did, of course, a measurement of the extracted gas and water flow and so on. And in this particular case, as I said, the control point was a transect placed down gradient of the contaminated site here that we assembled before doing the treatment and after, as I'll show you in some slides. And just before we go into the temperature, this is a couple of pictures that we're taking at the site. And as you can see, the footprint of such an operation is relatively large, because you have to have both treatment for water that is going into the boilers to make the steam. You have to have a lot of cooling equipment, and you have to have all these separators and vessels for carbon, etc., pumps and so on. So as you can see, this has a major footprint in this case. I would like to show you the temperature that was measured in this point TP3, and at this graph you can see here we have a blue line to the right and a gray line. The blue line represents the boiling point of PCE and water together. And for those of you who are familiar with the boiling point of TCE, it's 121 degrees. It may sound peculiar that when it's together with water, it boils at lower temperature. That's due to Dalton's law. So that's the fact. And the gray curve is the temperature, the boiling point of the water. And as you can see, when you go deeper in the groundwater, when the curve there is tending to the right, the temperature, the boiling point increases, and at this level 24, it's approximately 125 degrees. The red line that you are seeing is the temperature actually measured at this point at different dates that is running. And when the temperature is above the blue line, we are sure that there are no more free phase left in the soil. And as I said, if you want to go to sub ppm level, you have to be sure that the temperature is above or at the boiling point of water. And as you may saw earlier, the temperature reached that point to a time. The results on this site here was that we removed somewhere in between 1.5 and 2 tons of chlorinated solvents, and that depended a little bit on how you did your methods of calculation. But what you should take a special look at is how short the heating period was here. It was 25 days, and that's due to the fact that we can inject a lot of energy into the soil using steam. We did achieve the mass flux goal after 6 months, and the interesting thing here is that we have come back some years later. In 2014, the mass flux reduction was even higher due to the fact that the rest of the contamination there was almost gone. And as you can see, it was 99 or maybe even higher % reduction. This technique is rather violent, and you will see that you have very high concentrations when the temperature increases to around 100 degrees, as you can see in the upper graph there. The next one was a thermal conductive heating remedy that took place in the capital region of Denmark, and it was carried out by Niels and Krüger, and I've borrowed the slides from them for this. And it has some really nice aerial photos, as you can see here, where the layout of the immersion heaters that was used here is very visible on the in the center of the picture here. And you have the treatment plant to the right in the small containers over there, just beyond the graveyard. And as you can see, the footprint of all the equipment here is much less compared to the steam. So this is an advantage of this kind of technique. And as you may think, there was some problems getting all the permits and so on because you were so near to the graveyard, but fortunately it all worked out well. This is a setup in an unsaturated glacial till. Here the contaminant also was PCE and originated from fur treatment in the building that you can see there in front of the church from this old picture here. And the installation was around 147 heater wells, which is much more than you saw before at the other side. So we have a much denser network of injection points due to the fact that the amount of energy that we can inject using this technique is much less per well. At this particular case, we did, or they did a lot of continuous measurement of temperatures. It was carried out approximately 7-8 years later than the other one I showed you before. So that has developed during that period. The remedial goal here was to clean up to 1 milligram per kilo in the soil and based on soil samples. So that was another way to do it. And the results out there, they removed, in fact, 2.5 tons of PCE. And as you can see, the heating time was much longer, and it's more gentle curve that we see in the concentration in the upper part of the graph here. The heating time at that particular site was 169 days. And in the bottom to the right, you can see the values taken from the soil samples. We have the red dots, which are the baseline before the remedy, the blue dots are the dots that were taken just after the remedy was finished, and the green dots were taken approximately 2 years after the treatment. And the criteria is the gray line, the dimmed line that you can see, and as you can see, all sample points obey to the criteria. The insert picture there is just another example that we did, in fact, the same as you saw on the front page. And in this particular case, it was also the groundwater that was the reason why we did the remedy, but there was a residential building and we solved a vapor intrusion problem there too at that particular site. The last example I'm going to show you here is a remedy that was finished last year, and at that particular site we used electrical resistance heating. It was also carried out for the capital region of Denmark, and it was Geo who was the contractor out there. And the picture here shows the site. You have all the electrodes that is used for the electric injection placed underneath the vapor cap that you can see to the left, and the gray houses that you have in the back there are transformers. And to the right, you have the treatment plant, and there were some cooling and vessels for carbon behind this container here. This was a setup that was performed in a saturated glacial till, where the other one I showed you before was unsaturated. It was TC that was the contaminant of concern, originating from the military. It's actually an old Air Force base out there. The area that was treated was relatively small, around 500 to 600 square meters, and we had 53 combined heater extraction wells there. So it's more or less comparable to what you saw before in the density of wells for injection of heat. The remedial goal here was to reach 0.1 milligram in average, and no sample were to be above 0.5 milligram per kilo of TCE. And at this site, we had a continuous measurement of the extracted gas using gas chromatography, which is very precise way to measure. The outcome of this was a removal of more than 200 kilos of chlorinated solvents, of which 180 kilo were TCE. And that was far more than expected based on the investigation. And that's a common thing that we observe in a lot of these remedies, is that the mass is bigger than expected. You can also see that this took very long time, 300 days in fact, and that was due to the fact that we had some problems with cold water coming into the area, and also the power supply were a little too little, to say it in that manner, because we couldn't keep up the temperatures all the time in all the places. The average concentration was met, but there were some small spots that didn't meet the maximum concentration required. So it was still a success, and we made a risk assessment based on what was actually found, and the site got closure there too. So some of the lessons learned from all these remedies are listed here. I'm not going into all of them, of course, but I want to focus on a couple of things. You have to be aware that minor damages of buildings and so on are hard to avoid. So budget for that when you make your proposals and so on. We see that in a lot of cases, as you can see in the picture here. Also, be prepared for surprises. There's always something unknown that is going to happen. And also, the last thing I'd like to point out on this particular one here is use contractors with a good track record, because this is not jobs that can be done by the local plumber. it has to be someone who is really good at what they're doing. And to wrap up with some conclusions here, we have had thermal remedies in Denmark for more than 2 decades now, and they have a very good track record, I should say. And nowadays we are able to reach 0.1 milligram per kilo for the chlorinated solvents in a lot of situations, if that's what we want, and that covers most geologies and so on. We can use all the 3 techniques. They each have their hotspot, so to say. So you just have to apply them depending on the geology and so on. And also the sustainability is better than ever, I guess, because there's awareness of that. And as I said, always be prepared for surprises. That means that you have to have an agile organization that includes both the client at the consultant side and the contractor. For sure, challenges will occur, and we have to deal with them relatively fast because we are spending time. And money relatively fast when we're doing these kind of remedies. And just to put in perspective, I borrowed this picture here from Niels Ploug from Kryer. It's not from Denmark, but it's a picture of an installation of a 52-meter long immersion heater in Sweden that they done recently. So you can go to very large depth as it's showed here. It's just kind of spectacular, I think. And with that, I would conclude and thank you for your attention and take questions.
Thank you, Thomas, for your presentation. So before moving into the Q&A period, I would like to remind attendees to enter your questions in the question box on the GoToWebinar platform, and also you can download the PDF version of the presentation from the handout box on the dashboard. I will start with the first question. How many active carbon filters are typically needed for an ISTD remediation of a contaminated site?
Well, normally we have for the gas treatment, you would have at least 2 in series. Sometimes you can have 3. It depends on if you have a lot of, for instance, vinyl chloride. You have a polishing filter in the back, so that is maybe 2 or 3. And for the water, it normally is 1 or 2 filters. And again, it depends a little bit on how much mass is going to be extracted and how fast it is coming, but I would say 2 to 3.
Thank you. There's a question here about the first project, the steam remediation. What was WSP role in this project?
Well, in fact, we both did the design there and also oversaw the contractor work. So, but it was made when we were Orbicon, so it's a long time ago. But we, in fact, did the design there too. Today, normally the contractor do the design due to liability reasons, and we just, or not just, but we oversee what is carried out and also take samples and control and all that kind of stuff. So, so that was the role we did at that particular case.
Thank you. The examples presented appear to be in-situ thermal remediation methods. Are there any examples of ex-situ remediation thermal methods?
Yeah, but it's haven't not been used very much for these low temperature applications. The examples that has been performed is in the high temperature range, and I'm not covering this in this talk, but it has been used ex situ for mercury, for pesticides, and so on. So there are examples.
Thank you. Do you use only electrical heating, and if yes, why?
No, there are. We have also been involved in using gas as the source for thermal desorption. In thermal conductive heating, you can use gas burners for that to heat up the soil as well. So there's a choice between those, and normally it comes down to what is available and the price of a given project given by the contractors.
Thank you. For the project that were presented, how was the remediation method chosen?
Well, it depends on which one of them. The last one was just set up as a demand that the contractor had to use a thermal method, but there was no obligation for them to use either ERH or TCH. It was based on the best offer, which it included a model for evaluation, of course, where price paid a large amount of the value there. So it's basically a value or a price question.
Thank you. What are the unit costs for the treatment, and is it related to the size of the project? I think you just mentioned this, but if you can elaborate more.
Yeah, in general, it's the bigger the project, the lower the unit price. And in Denmark, we are right now having unit prices probably in the range between 300 to 400 euros per cubic meter. But it's there's a lot of factors that has to be weighed into that, of course. If it's below buildings where there's might be people working or something like that, that will increase the price. And if you have an open space, as I showed you in the last example, that will lower the price. So, but typically somewhere in that range.
Thank you. Are there any geological conditions that is hindering a thermal cleanup?
Well, we like not to go where there's a lot of organic stuff in the subsurface, like peat, because we get a lot of subsidence there if we treat that. So we tend to avoid those kind of soils with very high organic content.
Thank you. Lots of questions. The next one is for high temperature in-situ treatment. What is the minimum hydrocarbon contaminate concentration per kilogram of soil that this method can treat?
That's a very good question. I mean, in reality, it's a question of how much you will spend on treating the soil, because it's a combination of the temperature that you achieve and the time that you heat it. If you go to high temperatures and you treat it for a relatively long time, you can get below ppm levels. Also for the higher hydrocarbons, there are examples of that. And as clear that I showed you the last picture here, they did a pile treatment of dioxins in Vietnam a couple of years ago, and they got very, very low. It's the PPT level. That's not hydrocarbons, but it's organic compounds with similar boiling points and so on. So you can get very, very low if you're offsite. And that is also due to the fact if you want to go to high temperatures, you have to be sure that all water is removed from the soil, and that can be very hard to obtain, at least in a lot of in-situ situations. If you want to go high temperature in-situ, you really have to be careful in your characterization and so on about the conditions in the soil.
Thank you. I will take the last question. Which of the methods that you presented has the largest potential?
Yeah, that's a nice question. I think that thermal conductive heating, either with gas or with electricity as the energy source, has the highest potential, because we can use it in a broad range of temperature, and we also can use it in very different geologies. But of course, you have to be very careful about cold water coming in, and there can be some in very high velocity sites. You have to be very careful that you have control on your water. In that particular case, I would probably use steam if possible, but I mean, I think the greatest potential is the thermal conductive heating.
Fantastic, thank you. So we're at the end of our webinar session. Please feel free to follow up directly with Thomas via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you very much for your time, and thank you, Thomas, for a fantastic presentation. Thank you.